So where do we leave off? I think we're gonna let's compare these write functions. So this is a read function, but let's look at this write one. So their write function, they being this older code, jump to TE. These are such bad label names. I feel like this has to be my code. This is probably from the time when I was like programming in TI-89 languages too, where like reusing variable names. But anyway, so let's see. Does this use? So this does use a push mechanism. So let's see. So first it moves CX into AX. So we're printing the value that's in CX. Whereas what we were printing, we weren't using CX. I don't know that much. We're printing the value in AX. Actually, can I do a split screen in this thing? There they both are. Right at the bottom. So this one's less instructions, but that's probably mostly the difference between this one only pushes and pops what it needs. This has the proc directive, which I think that's just a directive for the assembler to tell it, hey, this is a procedure, by the way, if somebody uses this symbol. Because it also looks like it uses colons for the labels, but probably proc to say, oh, this is an exportable symbol. So these labels might have automatically been calculated to be local. This has more points it jumps to. Let's see. So first thing we do is move CX into AX, which is interesting because we just start with it in AX. I think we were going to put a move CX into AX, and then we're like, oh, let's just make the person using it put it in AX. So move CX into AX. Then they move 0 into DX, which I think we do. Yep. We do 0 into DX. Then we push DX, which is what we do here. Then we move 10 into BX, which is what we did at the beginning. So this pushes the... So here we loaded 0 into DX, so that then when we have this push here, because see, we push DX here, or this guy pushes DX here and here, so it ends up pushing it twice. So this actually looks fundamentally to be the same exact code, and like, even though I had this one open, I did not look at this until now. So, I mean, I'm sure I looked at this. I may have written this 20 years ago, but I had it open just in case I needed to reference it. And I mean, we referenced it a little bit, right? We looked to see that it was using int21, and I was like, oh, I don't want to use that then. So the interesting thing is this, because it had int21 available to it, it could have built a string, right? And then printed that string, and that was kind of what I assumed it was going to do. Doing the same thing with the stack, which it seems like the kind of thing I'd do. I have sort of a soft spot in my heart for fourth and reverse Polish notation and stack operations. It starts the same way, and then it does the division right away. And then it takes dx, which has the remainder, and adds 30 to it, which is... Now, we also put on the tty command, whereas probably doesn't have to be done over here, because int21 is different, right? Take a quick look at that. So if we look at int21, which I know we have here somewhere, so it looks like we're doing int21 with AH at 2. So function 2 outputs a character. Yeah, so it doesn't really care about anything else, right? There is no, there aren't all those parameters that we had to set. So the DOS version of outputting a character is a little more straightforward. So the other thing too is this. So this is going to standard output, whereas we're printing to the screen. So this one, that means, could be redirected to like a file. You're using DOS, which has a full concept of files, whereas BIOS is not an operating system, so it doesn't let you output to standard out. So they don't need this EH. 30 is fine. Then we push it, and once again, it's pushing the whole DX register, even though we really only care about the low byte. A lot of these DX operations could be DL operations, but it doesn't really matter. It's still going to be, it's not like the byte operations are going to be that much faster. So then it comes through, and so we push that. After we add 30, we push the value. Then we erase the value, which we're going to push and then erase over here. But over here, we do the comparison first, and then they jump greater than 0, whereas we jumped not equal to 0. We're treating this number unsigned, though. If it's not 0, it's greater than. This one could give us a weird situation in if you had a large. Nah, it'd be fine because this is doing an unsigned division, and after you've divided it by 10 once, you're not going to be a number that could be confused for being negative. So, sure. I'm sure there's no instruction cost cycle difference between not equal and greater than. Let's look it up though. Why not? While we're here, jump not equal. That is 16 or 4 clocks. It's probably based on whether it jumps or not. And jump greater than is 16 or 4 clocks. So, basically the same. So, unlike ours, where we do this move here, as we transition from the push to the pop phase, we have a move to get that last value. The code over here pushes that value, and then it pops every value. So it had to actually do an extra pop to handle the transition. So rather than saying, oh, we're going to push every value and then the last value, when that's in DX, rather than pushing it, we're going to wait and then just print it. What it does is it pushes it, compares, says, oh, we actually needed that value, and then pops it. And it erased DX and didn't need it. Like, it put a 0 into DX here that it didn't need to do in that case. So it basically overwrote the value just so it had to pop it. I mean, it needed to pop it anyway to keep the stack alignment right. Okay, so then after it pops it, so this sort of, you can imagine like this A loop through here is the push the values onto the stack. So this is very comparable to this one here. Then they have a little preamble to print the first value, and then they pop the second value, check to see if it's 0. So if this is 0, oh, it's going to print. So that's probably why it unrolls everything one, to make sure that it puts a 0 on. Something has to get moved here and printed. If your first time through, if you were given a 0, this is going to be 0. So you're just going to go through and print a 0. Whereas here, it was unrolled to make sure that you'd at least get that first 0 in there. So this then cycles through. Okay, so we're going to jump past this. We're going to jump down to C here. Once we get that 0 that we initially put on here, right? And so there's not going to be a 0 on. This, again, has, because it's putting the 30 on before it pushes it, we know that there's not going to be a 0 in the stack until it gets to this 0 that we initially pushed. Oh, you know, no, this preamble doesn't. This preamble just pushes the 0. We just always push before we compare up here. Whereas here we pop and compare. I guess it just knows that the first value it's going to have pushed twice, so it can unroll that loop. Because I just don't see what these two do. I mean, I guess it saves you a comparison, which is maybe a little faster, but more code, right? Like, because we could have just done this. That first value you pop isn't going to be 0. It's going to be 30 plus whatever you pushed on. Just two completely unnecessary instructions. But it saves you one compare in the course of printing the whole thing. Maybe worth it. Of course, we don't do that. Oh, we don't want to do that, though, because the 0 could be the first thing. And then this just continually loops here. Then jump to C, which prints new line, a line feed, carriage return, which, interesting. So up here, they're doing a carriage return line feed in the right order. Here, they're doing it in the same order that they were in here. So that's probably more evidence that I wrote this code. It's just weird. And then it pops the registers it needs to pop. So it's actually fundamentally very similar to this. A couple things different. The big ones being it's obviously using standard out rather than the teletype command, and so because of that, it only adds 30 instead of E30, and push before compare, so it can pop twice before the compare. Whereas here we just use the move, which saves us push and pop, so one less stack location gets used. Not that that's the huge amount of memory resource, but it makes it a little faster. And then this guy pushes all the registers, and I think it actually uses them all, A, B, C, D. Yep. Whereas this code here, this doesn't even use C, so we could have just pushed A, B, D, which is, I mean, that's probably, if we really wanted to make this right number a little more efficient, replacing push num, or push A and pop A with the explicit push and pops. It would use more memory though, and we are in a memory constrained area. That would have been that. So, and then we obviously have this exit proc, which just saves us even more memory, because then this guy would have to push and pop his own values, because he's pushing different registers, right? Because this guy only uses, he uses A, he also uses DI. He uses A, B, and DI. I think we'll call that a comparison of these two files. So that shows that our right number function here is certainly similar to that. I had a lot of similar ideas, and I was uncertain when I saw this before if I had written it or not, but now that I've looked at it more carefully, this has like younger me written all over it. So I'm fairly confident I wrote this. I mean, these are just weird. Like, who would name this TE? Maybe somebody named Ted. It probably, I'm sure it meant something to me at the time. I found that this moves it from CX to AX, but then it really does all of its work in AX. So this probably just had the instruction tacked in here to align with something else that maybe was going on. Because that's the only place where CX is used in here, right? It's almost like I don't even know why this thing pushes CX. It doesn't really use CX either. So that's enough analysis of that one. I think we're going to close this file and let's never look at it again. So I probably should save this as a session, just in case I ever want it again. Save session as. Nice. Okay. Next time we'll clean this up, and then I think that's it. We'll be done. Have fun out there, and good luck.